Calculus video 49, an example of curve sketching. So this time from the top, we're going to find all the asymptotes, the vertical asymptotes, horizontal asymptotes, the y-intercept, the roots, all that goes back to algebra. We learned those in algebra. The local and absolute extrema, the intervals of increasing and decreasing, constant if there is one, intervals of concavity, and inflection points, and then we're going to sketch the graph. So the whole thing, one big problem. Okay, our function we're using this time is g of x is equal to 6 over x squared plus 6. Let's start with the y-intercept. Again, the y-intercept happens when x is 0. So when x is 0, we plug that in, we get 6 over 0 plus 6, so 6 over 6 gives us 1. We get a y-intercept of 0, 1. Now, for roots, remember that roots occur when the curve crosses the x-axis. There are x-intercepts, or roots. X-intercepts is another word for this. X-intercepts. Since it's crossing the x-axis, intercepts, the y value is 0. So to find the roots, you let y equal 0 and solve for x. Alright, so if we let our y value, or our function value, equal 0, then we have 0 is equal to 6 over x squared plus 6. The only way we're going to get 0 out of that is if the numerator is 0, right? 0 divided by something is 0, but 6 equals 0 doesn't make sense. 6 is not equal to 0. There's no value of x. This means that there's no value of x that you could plug in here and get out an answer of 0, because you're never turning that numerator into 0. Therefore, no roots. What does that mean? No roots means the curve does not cross the x-axis. Okay, so that's some information. We know that the y-intercept is at 0, 1, and we know that since there's no roots, the curve does not cross the x-axis. Now let's look for vertical asymptotes. Vertical asymptotes. Now, vertical asymptotes occur when we divide by 0. When we divide by 0, and the original function divides by 0. So that's going to occur whenever my denominator is equal to 0, which occurs when x squared is equal to negative 6, which doesn't happen. I mean, if you want, you can say, well, that occurs when x is equal to plus or minus the square root of negative 6, but that's plus or minus root 6i, which is imaginary. That's not a real number. Therefore, no vertical asymptotes. So no roots, no vertical asymptotes. How about horizontal asymptotes? Horizontal asymptotes. VA here, vertical asymptote. Vertical asymptote. Again, that occurs when the denominator is equal to 0. And HA, horizontal asymptote. Okay. If you remember, there's 3 rules for horizontal asymptote, and they all have to do with the degree of the numerator versus the degree of the denominator. The horizontal asymptote you're thinking is what happens to the function, to the y value, when x goes to infinity or when x goes to negative infinity. Think about what happens when x gets really, really large. In our function, if x gets really, really large, remember the function here is f of x is equal to 6 over x squared plus 6. If x is really, really big, if x is 1,000, if x is 1,000,000, what's happening? I'm getting 6 divided by 1,000,000 plus 6. Well, that's going to be a very small number. And what we're going to see is, as x gets really big, the y value, the function value, goes to 0. And the rule here is if the degree of the denominator, in our case that's x squared, degree 2, is larger than the degree of the numerator here is 0 because there are no x's, so the degree of the denominator is larger than the degree of the numerator, we get a horizontal asymptote at y equals 0. And this also goes back to when we did limits, right? If we let the limit as x goes to infinity, that's what we talked about with horizontal asymptotes. Same idea there. So we will get a horizontal asymptote at y equals 0. HA at y equals 0. Because as x gets really large or negatively large, the function value goes to 0. All right, so asymptotes, y-intercept, roots. Okay, so that's kind of all the algebra stuff that we should have known coming into the class. What we have here so far, this is just a so far graph. We'll get more in a little bit. We know that we have a y-intercept here at 0, 1, and that we have a horizontal asymptote at y equals 0. That the curve should get close to that horizontal asymptote as x goes to infinity or negative infinity. Okay, let's keep going. The next thing we're going to want to find are the local and absolute extreme. Actually, maybe one more thing. I didn't ask for it, but it's not a bad idea to see what is the domain of every function you're thinking about, just in case, you know, there might be parts of the graph where the domain does not exist, or parts of the x-axis, the real line where the domain does not exist. In this case, the domain is going to be everything except for if you take square roots of negatives or if you divide by 0. But like we found out with the vertical asymptotes, having no vertical asymptote, there's no x value that you could plug in here and square it and add to 6 to get 0. When you square something that's positive and then add plus 6, you're not getting to 0. So the domain here is all real numbers. All real numbers. Okay, so asymptotes, y-intercept, roots done. Let's do local and absolute extrema, intervals of increasing and decreasing constant. All that will be coming from the derivative. So let's find the derivative. The original function is 6 over x squared plus 6, I believe. Yep. The derivative then, f prime of x, you have two options. You can do quotient rule, or you can bring that x squared plus 6 to the numerator. Either way is fine. I'll just go ahead and do quotient rule here. All right, if you brought it to the numerator, you'd be looking at like this: 6 times x squared plus 6 to the negative 1. I don't know, maybe that way is easier. Maybe we'll do that way. We'll bring it to the top, make it x squared plus 6 to the negative 1, and take the derivative. If we do that, we'll do chain rule. We'll take that negative 1, we'll bring it out front, and so it's negative 6 now. It's x squared plus 6, subtract 1 from the exponent, so now we're at negative 2, and then multiply it, chain rule, by the derivative of the inside, multiply it by 2x. Which is negative 12x over x squared plus 6 squared. Which is the same thing you would have gotten if you did the quotient rule. That is f prime. I'm sorry, I'm writing f prime. I believe that the original function was in terms of g. So let me kind of fix that a little bit. These were all supposed to be g's. G prime. Okay, so that was g prime of x, first derivative. Okay, so the critical points. We'll need to find critical points. Critical points occur when the first derivative is equal to 0, or when the first derivative is undefined. So when is the first derivative equal to 0? That would occur when the numerator is equal to 0. That will occur when negative 12x is equal to 0. That one's not too bad. We'll divide by negative 12 and see that happens when x is equal to 0. Okay, critical point right there. Critical points also happen when the derivative is undefined. That's, in this case, going to occur when my denominator is equal to 0. Because if you divide by 0, that's undefined. And if I take the square root, I get x squared plus 6 equals 0. That's square rooting both sides here, right? Square root this side, square root this side. You still get 0 over there. And it looks like we're still getting that same x squared is equal to negative 6, x equals plus or minus root 6i. So imaginary, that means it's not real, so we're getting no critical points from here. No critical points from here. So the only critical point I have is at 0. Okay, let's see if this is a relative extrema or not. So the question is the critical point at x equals 0 a relative extrema? I think I called them local. Let's stick with local. A local extrema. Question mark. Okay, to do that, we'll take the first derivative, f prime. We're not bounded here, so it's all the way from negative infinity to infinity. Here is 0. We need test points on either side, so let's go with negative 1 seems like a good one, positive 1 seems like a good one. Test points. Okay, so what was the derivative? The derivative function was negative 12x over x squared plus 6 squared. All right, so f prime of x, g prime, g prime of x is equal to negative 12x over, I've forgotten after all that, negative 12x over x squared plus 6 squared. So we're going to take our test point and see what is g prime of negative 1, what is g prime of 1. Again, what we're doing here is we're saying, what is the slope at those test points? Is the slope positive or is the slope negative? That's going to tell us increasing versus decreasing, or perhaps constant. If we plug in negative 1, we get negative 12 times negative 1, that's 12, over negative 1 squared is 1, plus 6 is 7, over 49. 12 over 49, but that's not really what's important. What's important is that that is positive. Positive. So at negative 1, positive. We're going to be increasing here. Increasing. Then at 1, we have negative 12 over 49. That one is negative, and we're decreasing after 0. So increasing before 0, decreasing after 0. Increasing before 0, decreasing after 0. That means 0 will be a relative max, or local max. All right, so information is we have increasing from negative infinity to 0, decreasing from 0 to infinity. Okay, decreasing 0 to infinity. We have a relative max at 0, comma something. And relative min, we don't have any. There are none of those. There's no place where it's decreasing and then increasing. So in order to find the y value for our relative max, remember that that is plugging it back into the original function. Our original function here is, I should memorize these better, 6 over x squared plus 6. F of x is 6 over x squared plus 6. We've already plugged in 0 once. That was the y-intercept. We got 1 as an answer. We get a relative max at 0, 1 at the y-intercept, and a relative min, none. Okay, so we're starting to get a little bit of an idea here of how this graph looks. So far, again, still not done yet. So far, we have this. We have a horizontal asymptote at y equals 0. We have a y-intercept over here at 0, 1, which is also a relative max. We know that's around its neighborhood is at least the highest point. There's no relative minimums. So what does this look like? Well, I don't know exactly, but I'm pretty sure you're going to have something kind of like that there, because that is a relative max. And I'm pretty sure we're going to just kind of go out towards this horizontal asymptote, because that's what curves do. They get closer to those horizontal asymptotes as x goes to infinity or negative infinity. We just need to kind of decide what happens in the middle here. Something else we know. We know that the curve increases from negative infinity to 0. So we know that although I may not know exactly how it looks yet. We know the curve is going to increase from negative infinity to 0. And we know it's going to decrease from 0 to infinity. So my best guess so far is that the curve looks something like this. Okay, let's find more information. Let's go back up to the top. We have found all the asymptotes, vertical, horizontal, slant if there was one, but there's not. A y-intercept and roots. We've got the local, and we have not done absolute extrema. Okay. Well, if you remember, the absolute extrema occur on, you have to check the relative or local extrema, and we have to check the endpoints. We don't have endpoints here, so since there are no endpoints, we just have to check the local extrema. So let's do an absolute extrema. And absolute extrema, we're checking two things. One, we're checking the local extrema. And two, checking the endpoints. And by checking, what we're saying is we're taking those values, the local extrema and the endpoints, and we're plugging them into the function, and we're seeing which one is the highest. That's the absolute extrema. Which one is the lowest? Which one is the highest? That's the absolute max. And which one is the lowest? That's the absolute min. Well, no endpoints in this particular case. This thing goes from negative infinity all the way to positive infinity. No endpoints, so I don't have to check those. The only local extrema I have is I have a local max at 0, 1. Well, if that's all I have, then my absolute max must be at 0, 1. And we're not going to get an absolute minimum. There's no local minimum to look at, and there's no endpoints. So we will say absolute max 0, 1, absolute min, none. And it might be weird to think we have no absolute minimum, but take a look at the graph that we drew. We feel hopefully pretty confident about. The curve is getting closer and closer to that horizontal asymptote at y equals 0, but it never actually reaches there. Therefore, no matter what point you pick, there's another point further down the line that's a little bit less than that. And then another point further down the line, it's a little bit less than that. There's always a point that's a little bit lower than whatever point you pick. Therefore, you never actually reach a bottom. It never actually gets to 0. It can just get as close as we want. All right, so we've done the absolute extrema. Scrolling back to the top here, that part is done. Now we have intervals of increasing, decreasing, constant. And we did that one already as well. Intervals increasing, decreasing, none on constant. Now intervals of concavity and inflection points. For that, we need the second derivative. Let's take a look at our graph so far. If I'm looking at this curve, here's what I'm seeing. I'm seeing on the very far side, left side over here, I'm thinking this is going to be concave up. It looks like kind of very slightly concave up, but concave up nonetheless. So that's a bowl curving upward. Right, I'm going to say that this is concave up based on what we have so far. I'm just guessing at this point. And then I'm going to say it's going to switch. And in the middle here, it looks concave down. It looks concave down. And then I think it's going to be concave up again. That's my best guess based on how the curve looks so far. That would make sense based on the graph. And then it looks to me like we're going to have two inflection points. It looks like we're going to have an inflection point about right here, and it looks like we're going to have an inflection point about right here, points where the curve changes concavity. Concave up to concave down in this case, and then concave down to concave up. We need to find out what those inflection points would be. What are those x values where it changes concavity so that we can put those points on there. Okay, so we think that's what's going to happen. Let's actually see if we're right. So concavity and inflection points. If we remember, the original function was 6 over x squared plus 6. Then the derivative function I'm using f again. I need to go back to g's. My apologies. Okay, so the derivative was negative 12x over x squared plus 6 squared. Okay, what we need to do to find concavity and inflection points is to find the second derivative. So, second derivative, again, you could use the quotient rule, or you could bring that x squared plus 6 squared to the numerator and think of that as negative 12x times x squared plus 6 to the negative 2. Honestly, either way is fine. In the first way, you're using the quotient rule here, right? That's quotient rule. In the second way, you'll be using product rule, because your first function there, negative 12x, your second function, x squared plus 6 to the negative 2. Either way is really fine. Let's just try quotient rule this time. All right, so g double prime, that's the derivative of the numerator. The derivative of negative 12x is negative 12. Leave the denominator, x squared plus 6 squared. Minus, leave the numerator, negative 12x. Derivative of the denominator. So we'll bring the 2 down, right? The squared comes down. Then it's x squared plus 6 now to the first power. 2 minus 1 is 1. Times the derivative of the inside. The inside here, x squared plus 6. Its derivative, 2x. All divided by the denominator squared. Now it was already x squared plus 6 squared. And if we square that, now we are at x squared plus 6 to the fourth power. Before you take another step, think about what we have here and try and simplify. Notice that you have an x squared plus 6 squared here in this term, an x squared plus 6 to the first here, and an x squared plus 6 to the fourth there. Every term has at least an x squared plus 6. So I'm going to simplify by dividing every term by x squared plus 6. So that one goes away. This one takes 1 off, and now I'm at cubed. And this one takes 1 off, and now I'm at the first. And if you'll do that step first, the simplification here is much easier. Okay, so g double prime of x is negative 12, x squared plus 6 to the first now. Over here I have minus negative, that's going to become plus. 12x times 2 times 2x, that's 48x squared, and the x squared plus 6 canceled out, so that part's gone. Okay, plus, got my signs right. And then in the denominator, x squared plus 6 to the third. It's already looking better. Okay, distributing the negative 12 here and here, I have negative 12x squared minus, what is that, 72? It's 72. Plus 48x squared over x squared plus 6 cubed. That would equal, again this is g double prime of x, that is equal to 36x squared minus 72 divided by x squared plus 6 cubed. And that's about as simple as we're going to make it. So what we want to do is we want to find possible inflection points. Possible inflection points. And the possible inflection points will occur whenever g double prime of x equals 0 or g double prime of x is undefined. We need to check both of those things. When is the second derivative 0? When is the second derivative undefined? The second derivative is 0 anytime our numerator is 0, because 0 divided by anything except 0, possibly infinity, is 0. So I'm taking my numerator, I'm setting it equal to 0. I'm solving 36x squared equals 72. Divide both sides by 36, x squared equals 2. Take the square root. Don't forget x equals plus or minus the square root of 2. Right? Plus or minus the square root of 2, not just plus the square root of 2. All right, so if I want a decimal, I'm looking at about 1.41. So we have x equals plus or minus 1.41. These are possible inflection points. We'll have to put them on a number line to see if the concavity actually changes there or not. Then we'll look down here, when is the derivative undefined? The second derivative is undefined whenever x squared plus 6 cubed is equal to 0. Dividing by 0 creates undefinedness. Whenever x squared plus 6 cubed is equal to 0. Alright, well, let's cube root both sides. Alright, we'll cube root this side, we'll cube root that side. The cube and cube root cancel out. We have x squared plus 6 still equal to 0. This should look familiar to you. This gives us x squared equals negative 6. X equals plus or minus the square root of negative 6. X equals plus or minus square root of 6i. Imaginary. Therefore, no possible inflection points from here. Okay, so my only possible inflection points are at plus or minus 1.41. So let's get a number line going here with our g double prime at negative 1.41 and positive 1.41 with test points in between. So we'll have test points over here, let's say negative 2, less than negative 1.41. One at 0 in between, and one at positive 2. Just trying to pick nice numbers here. And we're asking ourselves, what is g double prime of negative 2? What is g double prime of 0? What is g double prime of positive 2? And what we're really looking for is the answer here positive or negative? Is it concave up or is it concave down? We're in second derivative, so we're in concavity here. All right, let's go back and remind me specifically what was the second derivative. 36x squared minus 72. So recall, g double prime of x is 36x squared minus 72 divided by x squared plus 6 cubed, if I'm not mistaken. Once again, let's take a look at the denominator. If you put any number and you square it, that's positive. Positive number plus 6, still positive. Positive number cubed, still positive. So our denominator is going to stay positive no matter what. We really just have to check the numerator. If we check the numerator, let's start with 0 because it's the easiest. G double prime of 0, 36 times 0 squared is 0, minus 72 is negative 72. Point being, it will be negative. All right, how about negative 2? Negative 2 squared is 4. 36 times 4 is 144, I believe. Minus 72 is a positive 72. So we get a positive 72 in the numerator, something positive in the denominator, and a positive divided by a positive is a positive. And lastly, g double prime of 2 is going to be the exact same answer here. 2 squared 4, 4 times 36, 144 minus 72, 72 over the same denominator, positive. So we get positive, negative, positive, which means because it's a double prime, this is concave up, concave down, concave up. And because we switch concavity at those points, we get inflection points here at negative 1.41 and inflection point here at positive 1.41. So let's write that information out. We have concave up. Concave up. Concave up was from negative infinity to negative 1.41 and 1.41 to infinity. And if you didn't want to use negative 1.41, if you want to do negative square root of 2, and for 1.41 do positive square root of 2, that is a little bit more accurate. Okay, concave down is from negative 1.41 to positive 1.41. And we get inflection points at negative 1.41 comma some y value and positive 1.41 comma some y value. How do you find the y value? We go back, we go back to the original function, f of x, nope, not f, g of x is equal to, I believe it was 6 over x squared plus 6. So we're going to plug these numbers in. Remember, this is actually square root of 2 and square root of negative 2. If you square that, the square root of 2 squared is just 2. And you get 6 over 2 plus 6, or 6 over 8, or 3/4. In both cases, you get 3/4 or 0.75. So we have inflection points at negative root 2, 0.75, positive root 2, 0.75. All right, that should be enough to do our final drawing, our final curve sketching. So let's make a nice big graph. Here's what we know so far. 0, 1. That's the y-intercept, but it's also a relative max. It's also an absolute max. We have a horizontal asymptote at y equals 0. We know that there are no relative minimums. We know that the curve does not cross the x-axis because there are no roots. There's no vertical asymptotes. We know that at root 2 or 1.41 and negative 1.41, negative root 2, 0.75 are inflection points. So maybe about right there and about right there. We know that it's increasing from negative infinity to 0 and decreasing from 0 to infinity. So I think our graph from earlier is pretty spot on. A curve that looks something like this. Here we have 1.41, 0.75, that's an inflection point. Another inflection point over here at negative 1.41, 0.75. And we have concave up. We have concave up on the right. And in the middle, we have concave down. And we have sketched our curve.